So I'll go ahead and get started. So we have two topics with regards to trees to take care of. The first is just I want to review Huffman trees a bit more. Mind if I'm going to go ahead and turn on the light back here. So a bit brighter. So we're going to go over just a bit. We're just going to review Huffman trees a little bit, okay? And then we are going to go over the traversal algorithm just one more time. Basically, this is the type of question you might be expected to see on the timed lab this week. So now, as far as the dates for exams, I was originally thinking maybe next week, but honestly, I don't see the point of that. Especially since I've gotten already a bunch of emails from 1068 students saying, "Hey, I've got all my other exams that week. Could you, if you're thinking about pushing it, please push it to April." So we'll probably do our exam on the 6th, and that will probably include. So that will go over essentially recursion. So we'll go over recursion, trees, but I repeat myself because basically all the problems that we'll do with recursion will basically be tree problems. Wondering why I'm not projecting, and that's because, well, I'm not connected. I mean, that's a pretty good reason. So trees, recursion, and then hash tables. So probably some questions on hash tables. Now, here is so we went over Huffman trees last time, and we're gonna just repeat what I said here, which is that Huffman trees, we use them for lossless compression, meaning that we basically can shrink a file down to a much smaller file. All right, so, and the idea here was, if we go to the slides, right, you can create a tree out of these things. And I think I did a couple of examples in class. I did some yesterday in the video I uploaded, but they're pretty. But I'm going to just do two more examples of those just so we can clarify them, because they will be on the exam and they will be on the final, and generally they're worth anywhere between, I think, 7 or 8 points for this kind of question. So remember, what it is that basically for every document we regenerate a frequency count of that document. You just count up all the characters, right? You just count up all the characters in the document. Okay? Now, why do we do... And we do this because rather than making every single character take the same amount of bits as we would in ASCII or UTF-8 or Unicode, well, UTF-8 is kind of the exception. It doesn't necessarily do that, but for simplicity's sake, let's just assume it does, right? All these characters, they take up the same amount of space. And the idea behind Huffman trees is that, well, since space is a really common character and E is a really common character, but J, Q, X, and Z are really uncommon, why don't we make those sequences take 3 bits, okay, and those uncommon sequences take more like 10 bits. And because even though those will be really expensive once we hit them, the savings we get on these guys, on the space, which is basically, again, every word, or E, which is really often, the savings we get from those are going to be astronomical. Right? And so we use this table and we build something that looks like this. Did I build the bottom part of this when I was on Tuesday or no? All right. I'll do that, and then I'll give another example. But remember, typically what we do is that every language is different, right? So, and every document is different, right? If, say, we're dealing with Gadsby, the novel without the letter E in it, in that case, well, the distribution is probably going to be different because he didn't use any words with an ED ending, so he used a lot of did. Words like did walk, so a lot more D's and a lot more I's, right, in his document. So that's, those frequencies change, so, we'll get a more optimal saving if we generate a unique tree per document. And what we do is that we count up the frequencies, and then then we do the encoding, and we send both this frequency table and the encoding, and then the other person can generate the tree on their end, and then decode what we sent. So it's kind of like encryption. The only difference between compression and encryption really is that we intend everybody to be able to uncompress something, whereas with encryption, we only want certain people to read what we read it. So here it's kind of like encryption in the sense that we're turning it into a bunch of gibberish, but the idea is that it's gibberish that anybody can take apart. So, all right. So suppose we've got this frequency table. Now I don't want to generate this entire thing because I'll probably make a mistake first off because that's a lot of different combinations. But say we are given this frequency table and we're given all the way up to V. Okay, so we're given ZXQJ, the frequencies for ZXQJ, K, V, and let's see. I'll do B, even though that my tree won't match after I do B, but I'll explain why that is. Maybe because generally that seems to give students a pretty good understanding of it. So suppose we've been given the documents, and let me just make sure that we've got, so X, Q, J, V. So suppose we've been given this document that just says these are the frequencies of how often these letters appear, K and V. K and V. Okay, I've done B and I've done K. So X, J. Oh, I missed Z. Right. How could I forget Z? So X, Q, Z, J, V, K. So 1, 1, 1, 1. This appeared 5 times. This appeared 8 times for the frequency. The first thing you do is that you typically take this frequency table and arrange and put them all into priority, and put all the symbols you have into a priority queue, ordered by their weight. Right. So X, Q, Z, and J all have the same weight. Now, if you got this on a question, question on the exam, you might go, wait. All those 4 symbols have the same weight. Professor, which one should go first if they all have the same weight? Did we even learn that in class? And it'll probably go something like, darn, I forgot about that. But we're going to be complete. But so what I would do in the test is probably I'll give you a rule, or I'll tell you it doesn't matter. I'll grade you because the shape of the tree will still be the same, even if the orders are different if they've got all the same. But so here I'm just going to use them. I'm just put them in the order that will match this this output. So I just put them in the order that will match that output, which doesn't really make sense to me, but whatever. Okay. But otherwise I might give you a rule like, well, if they're all in, or if there are things with a matching with multiple weights, then arrange them in alphabetical order or something like that. So, but the algorithm from here is pretty simple if you remember how to do it correctly, which is that we start building a tree from each of these guys. And what we've got here is a priority queue. So we dequeue the first 2 things in the queue, which is X and Q. The first thing off becomes the left node, and the second thing off becomes the right node. Of course, while we all the way on the other end. So we dequeue X and Q, X, Q, and they've got a combined weight of 2, right? So now then what we do is that we reinsert this into the priority queue, okay? Now, because it's a queue, right, normally you just place it right over here on the end. So let's just call this XQ. I know it's super small, but it's got a combined weight of 2, and that's the important part, right? So now, however, this is where most students make a mistake, which is that they forget that this queue is a priority queue, right? Which means that when you add something to it, it doesn't end up in the front, or it doesn't end up in the back, but it gets reordered. Everything gets reshuffled in there, basically in the order based on the weight. So here it skips ahead of B, and we get, and it comes behind Z and J because it's now 1, 1, 2, 5, 8 as opposed to 1, 1, 5, 8, 2. So now we do Z and J. Notice that basically they're in completely separate trees at the moment. That's perfectly fine. All the algorithm cares about is that we're dequeuing and combining, essentially. So you just draw that, and they'll have a combined weight of 2, right? So this was the one with X in it, and this was the one with Z in it, okay? Which one should go first? Well, it's the Q, right? If we're talking about Q's, the one that was already there first should go first. So we don't necessarily swap them, but even if you did, I probably wouldn't take off points for it. I might not even catch it because the shape, so long as will probably still be the same, which is what I look at. Okay, so now you've got 2, 2, 5, 8. So now we pop off these 2 nodes and combine them together. And we've got a single tree that has a combined weight of 4. So we put that at the end, but since it's a combined weight of 4, it's going to go all the way to the beginning because it's the lightest thing. So now we've got 4 and 5 at the beginning. So 4 goes to the left, right, because it's the first thing off, and then 5b goes to the right. So that was 4 plus 5, which gives us 9, right? It's amazing how, like, you know, how hard very simple math gets in computer science, right? It makes you doubt everything. Okay, so now we've got 8 and 9. Sorry, we've got k and this big old thing. So now we do k and this big old thing, and we've got this tree here, right? Now, again, so let's just go ahead and check the answer we've got here on the slides. So if we match, if we match it up, we've got, did I swap the values of k and b? Hold on. Yes, I did. B had a value of 8 and k had a value of 5, so I swapped those. That happens. And if you show your work, you know, we'll be able to detect that on an exam pretty easily and probably like only take off a point. So let's just pretend that I didn't do that. So boom, boom. Right? How embarrassing. I've already done it right once though. So but notice that the shape is the same, right? And that's a lot of what we look for. So this entire tree has a combined weight of 21. Sorry, let's see. 4 plus 5. So no, not 21. 19, I believe. No, 8 plus 17. See, told you that math gets hard with simple numbers. So 17, that means that what symbols needed to be merged first? B, P, G, Y would all get merged first before we even started coming back to revisiting this guy, which if you look at the tree, right, that's what happens. B, P, G, and Y become their own tree, and then then this guy finally merges with W, and then this tree, you know, so we've got multiple trees building. So we're probably going to deal with only something that has like 5 or like only 5 symbols in it. Right? So let me go ahead and like generate like a problem you might see. So on an exam, the problem will be something of this form, like so given these symbols, typically what I do is it's a 2-part question. And the second part of the question, the first part is build the tree. The second thing is decode something in a message. Okay? And to decode the message, we grade you on that based on the tree you have, not what the correct tree was. Right? So you can get the second part correct even without the first part. But typically what we do is that, what I do at least, is that the second part should decode into some kind of English word, right? Or something, you know, fairly straightforward, so that basically if you get gibberish out of the decoding process, or if you are left with, or you have some leftover bits, you realize, hey, I built the tree wrong. Maybe if I have time left over in the exam, I should go back to this, right? Okay, so I might give you something like, let's see, so we've got W, R, D, Q, O, L. Okay, so I might give you something like this with 6 letters, and let's go ahead and figure out what the bits are, and I'll go ahead and put them in order. So let's say 1, 1, 3, 4. So 1, 1, 3. Let's see. Actually, let's go with 1, 1, 3, 7, 5. Sorry, 1, 1, 3, 7, and I can't really do anything too exciting there. 20, 21. I had a really good one I came up with on the fly over here, and 100. Okay. So let's go ahead and decode. Build the tree from this thing. Okay. So we've got W and R. They're the first things that need to come out. So we do that. Okay, and then we put the combined node in as 2. And this one isn't going to be, so this one's not going to be like anything too interesting, unfortunately. But the other one was, so let's see, combined node of 2, then 2 and 7. So, sorry, 2 and D. So that has a combined weight of 9. So 9 in Q. So 9 and Q has a combined weight of what? 29. So that means that we've got a 29, and that gets inserted into here. 29, right? So now we've got O and 29. So O and this thing, which has a combined weight of, so that was 21 plus 29, so 50. So now we've got 50 and 100. Means that we've got L over here, which is all the values in the tree, right? So now what we've got is something like, so we put all, so how do we know what to decode, if we need to decode something, if we've got a message, 0's on the left, 1's on the right. And typically we'll have a tree that maybe has just a slight thing like this, like a slight zag to it, as opposed to just all the letters being on the left or all the letters being on the right. But that's typically a mistake when we see that. But so let's see what your message might be. You might get something along the lines of, get something along the lines of 0, 1, 0, 0, 0, then 0, 0, and then 0, 1, 0, 0, 1. And then, let's see, what else do we have? 0, 1, 0, 1. Right, so you might get something like that as your message and be told to decode that. And so what you do is you just follow the zeros and 1 from the root, so until you hit a leaf. So 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, that's W. 0, 0, so now we go 0, 0. Now we know to stop at this one, stop after 2 because we've hit a leaf now. O. 0, 1, 0, 0, 1, it's an R, and then 0, 1, 0, 1, so 0, 1, 0, 1 gives us D. That gives us word. So, and the fact that we didn't end up with like some gibberish word lets us know that that was what we want, that basically our tree was probably correct. Yes?
So you just keep going till you hit a leaf?
Until you hit a leaf, and then you start from the beginning. You go until you hit a leaf, and then you stop from the beginning again. All right. So, So the last thing I want to do, which is surprisingly that didn't come up in the chapter earlier, and I almost forgot about it last time, was suppose we've got a binary tree. Go ahead and delete this. Right now, I made a mistake when a kind of unintentional mistake, which is really nice when we were working on the tree, which is that I had a size variable. Actually, choose this. I had a size variable. I've commented it out because I realized I didn't use it at all. I didn't, right? When I wrote my add and remove methods, I forgot to increment the size when I added something and decrement the size when I removed something. It happens. Okay, but that actually leads to a very good question, excellent question, which is that how could I calculate the size of the binary tree recursively? Okay, right? So, which means that basically I would ask you something along the lines on the test of writing a method like this. Here's a public, right? So here's the wrapper method, but here's the private int size method, which given a node, doesn't matter what kind of node it is, given a node with the root of a tree or a subtree. Given a node E that was the root of a tree or a subtree, come write a method that would return the size of it. Now remember, I said there are two algorithms that we need for trees that solve 90% of all tree problems you're going to encounter. The first one is the ones we used on add, remove, and contains, which is that, okay, we're given a value, and I'm going to go left and right until I find that value or something, right? That's what that one's going to do, right? I'm going to go left and right until I find all the nodes that are smaller than that value, that have this value in it. So basically, when you're searching for something specific, you go like you do the whole comparison to the root node and then go to the left subtree or the right subtree, right? That's one of the algorithms. That was what was done for the add and remove method. For the other ones, I said it's the traversal algorithm. It's the, if we remember all the way back a couple of weeks ago, let's go ahead and just pull those up, right? The traversal algorithms, right? They're the ones that, right, they're pre-order, post-order, and in order. In other words, we visit all the nodes of a tree, okay? We visit all the nodes in the tree, and we go, and all that differs with those three algorithms, the order we go in. We visit the left subtree, we visit ourselves, and we visit the right subtree. And visit here, we need to interpret that very loosely. In other words, it means do some operations on the entire left subtree, do an operation on myself, do an operation on my right subtree. Okay. Right. So this is the algorithm that we can adapt and use to solve a lot of the problems that we have with trees, like count the number of nodes in the tree. In other words, the one we're solving on right now. Or you given a tree of that holds strings in it, count the number of strings that count the number of strings stored in the tree that are bigger than 5 characters. Right. That's another thing you can do with this kind of algorithm. Or calculate the sum of all the even numbers stored in the tree. This one was a test question on my very first semester here, and I felt that basically that it's worth going into, because if you know how to do it, you can do it in 4 lines. I give you an entire page where it takes 4 lines. Most of these things are actually fairly straightforward. You can do a lot of things recursively just by calculating the answer from your left tree, your right tree, and yourself. So let's figure out how we would calculate the size of a tree recursively. So if it's a recursive algorithm, we need 2 things. What are the 2 things we need? What are the 2 parts? Yep, base case and the other one, right? The recursive case, right? Recursive algorithm, recursive case. So we need the base case and the recursive case. So we're given. So what's the base case for all of our tree algorithms, essentially? Sorry? Base case for all the tree algorithms. When is the answer really simple? Yes? When the root is null. Okay, so let's use that as our base case. That sounds really simple. So what should we do? What's the size of the tree if the root is... what's the size of the tree or subtree if the root is null? 0. Yeah, that was easy, right? If root equals null, return 0, right? Got nothing there, right? Calculate the size of this tree, in other words. It's 0. Okay, right? So otherwise, we're given a tree that looks like this, and don't really need to zoom in for this one on the recording because it's pretty easy, right? So I'm just using the abstraction of 2 subtrees over here, right? We have a triangle and another triangle, meaning that this is a left subtree of an unknown size. This is a right subtree of an unknown size, right? Okay, and this is the root node, and this is the local variable root, okay? He might have parents, he might not, whatever, okay? We're just looking at this from his perspective. Okay, so from his perspective, what is the size of the tree? How can we figure that out? So, and the key, remember, is to do a traversal. So first off, what are the 3 parts of a traversal algorithm? Okay. What were the 3 parts I went over? Anyone? Yes.
So, depending on which.
I mean, it depends on the order, right? But what are the 3 parts of those?
The left, the right, and then the root.
Yeah, left, right, and root. Okay. So we split. In other words, that means we need to split this up into 3 parts. Okay. So the 3 parts are figuring out what the heck's going on with the left side, what's going on with the right side, and what's going on with ourselves. Okay. So let's figure out ourselves. Okay, what's going on with ourselves? Lots of things. But but from the tree's perspective, what was he interested in? The size of his self, right? Okay. Is what? What's my size? Like me as a single node. 1. My size is 1. Okay. Okay. So now let's figure out maybe the size of my left tree, right? Figure out myself, figure out my left child, figure out my right child. This is the pre-order way of doing it. So what's the size of my left child, of my left subtree? Remember, we're in the recursive case here.
Size plus his left.
Yep. Size of root dot left. Okay? If it's null, it's going to give me 0. Otherwise, if it's not null, what's it going to do? It's going to return 1 plus the size of its left plus the size of its right once we tell it to calculate int right size. Once you see it, it's like blindingly easy. Dragging it there, not easy. So don't worry about it. So now we've got my size, my left side, my right side. Now we just return my size plus the left plus the right size. Okay? And this makes it a really easy thing to do. You just have to basically solve the problem. So all these algorithms are pretty much that you can expect to see are pretty much, okay, figure out what the base case is, which is pretty much almost always, what if the node or nodes we're asking about are null? Okay? The other ones are figure out, like, solve this problem locally, complete my small portion of the problem, be it figuring out if if my data is an even integer, right? If we're counting the number of even integers, or if we're summing up the even integers, figure out if my thing is even and set my value equal to that if it is, otherwise set it to 0 if it's not. Then do it for my left side and do it for my right side, and then combine those results together in a meaningful manner, right? Typically, it's counting things. Okay. So this kind of recursive algorithm is really easy, and like I said, you can do this in just one line by, of course, doing this. So return 1 for myself, then size root dot left, and then size root dot right. A bit messier, but you can get it down to 1, 2, 3, 4 lines that way in an answer. So these questions are actually fairly easy to solve, but the key is to remember that basically if I tell you to do something and I give you a node, right, that's the root of a tree or a subtree, then that's a pretty good indication you should solve it recursively, right? And if you can solve it recursively, that's going to work. Okay, so you'll have a problem like that on your timed lab. So practice a problem doing this, and I guarantee you're probably going to hit something that's very similar to it. It's your timed lab is going to go over this and basically some basic stuff about heaps, right? And even if you don't remember how heaps work, I will remind you because I'm going to tell you, here's the steps for doing this. Implement them, right? It's not exactly meant to be the most arduous of arduous things, right? Okay. So with that being said, we've spent a half an hour here, and we are done with trees. We are done with chapter 6, which means we have the following topics left to cover for our class, which are we have to cover hash tables, sorting, and graphs, and we've got plenty of time to do that. I feel we're doing a pretty good pace here. So operating under the assumption that I will be out next week, you'll probably be using when you're here. This will be basically an extra lab section here in here. So be prepared to work on program, and it will basically be an application of what you know. And if I give you recorded lectures, they'll probably be, well, it might get into sorting, but sorting homework really isn't interesting. It's not. I've never found it fun to just implement sorting algorithms. The students don't really find it too fun either. What I'm planning for you guys, hopefully that will be fun. So let's go ahead and see chapter 7. So chapter 7 is about sets and maps. So just take this sweater off since it's starting to get hot in here. Okay. So I personally like this chapter because it goes over hash tables. Just like priority queues you build priority queues using a heap, use a hash table to build sets and maps. So so basically we're going to learn about an underlying data structure. And this part has, I feel more than other ones, has like 2 distinct parts, which is, and the book doesn't really go into one of them as well as it should, which is that basically it goes into a lot of how you build these things, but not much about how you use them, right? You can kind of get an idea of how you're supposed to use trees and stuff, but maps are a bit more, and especially sets you can figure out. And lists, of course, they're just like you'd use them basically anywhere you'd want to use an array. But But maps are a bit trickier. But once you figure out how to use them, you want to use them everywhere for everything. And the reason is because these things are constant time data structures with the way we implement them. Meaning it's constant time to add, constant time to remove, constant time to check if something's in the data structure. All those take constant time, which is of course quicker and more efficient than doing something like log n, which is like a tree, or doing O of n, which is what you'd have in lists. We use that using hash codes. You have to understand the benefits and performance trade-offs of two ways to implement hash tables. We'll go over that, but there's also trade-offs just for using sets and maps, or hash sets and hash maps. In other words, using those constant time data structures. And so there's two big trade-offs. Trade-off number one, you don't get to care about order anymore. Okay, so binary search trees, right? They cared about order. The order you stored in, what you stored in binary search trees, they had to be comparable stuff. Hash tables, you can store comparable stuff in them, sure, but you can also store uncomparable things in them. But from the hash table's perspective, none of that matters because order in the table does not matter. What it does on the back end is it doesn't care about order. Anything can appear in any order. It's just going to find it instantaneously, though. It's like having a magical mess, basically, that's just able to sift through. Okay. The other part that you need to know is that this big sacrifice of how we get this constant time, well, it's constant time. That's another caveat. It's constant time with a caveat, which is that sometimes you have to resize, which means it takes O of n time when you do the resize, just like an array list. Occasionally, it will take O of n time to copy it over into a bigger table. But the second drawback is that we're going to basically waste a bunch of memory as a feature. We are essentially going to burn a bunch of memory and say that is the sacrifice to the time gods that we are making in order to get constant time. Okay, so we are going to learn how to implement these hash tables, but first we're going to learn how we're going to see how you use them for maps and sets, and then we're going to see how we can use maps pretty easily. I will also be temporarily going into Python for a second because it's really easy to show how to use maps in Python. Maps in Python because they're called something completely different and they're just really easy to see how they work in Python. And then I'll switch back over to Java. Okay, so we learned all about like all these other collections and we learned about the list. And basically the big thing about lists though is that they have indices, right? That's what sets them apart from trees in one big way. They have indices and stacks and queues. Stacks, queues, and trees, they don't have any indexes, right? They don't have any of those things. Okay. So the list has this index collection, which means that you can you have an index associated with every element. Okay. You say, here's the index I want, and it'll give you this value back. Okay. Now searching for something like that is a linear time. These are going to be constant time that we do. So let's talk about sets. Sets are not indexed. They have no indices. The order doesn't matter in a set, but you do constant time retrieval of their information, and you can remove elements without having to bother shifting stuff over. So let's go ahead and just get on the same page because you're wondering, oh God, is this like a weird kind of thing? Like, are we bad at naming things now? No, we are actually still marvelous at naming things, just unlike historians. We actually do manage to get sets correctly. Sets are literally mathematical sets, which if you've taken the prerequisite class to get here, which is math concepts, then you know what a set is. Congratulations, you know what this data structure is and how it works, but I will review it anyway, just to make sure we're on the same page, right? Okay, this is, let's go ahead and create set A on the board. Set A is equal to the values 1 and 2. Okay, set B are the values 2 and 1. Are these sets equal in math? Yeah, they have the same elements, so they're the same. So they're equal. They've got the same elements, so they represent the same thing. Their Venn diagram is a circle, right? You know, they are the same thing, right? Okay, so now if I change it to 1, 2, 2, 1, 3, it's, you know, a different set, but it's the same as, but the order here doesn't matter. It could be 2, 1, 3, 3, 2, 1, 1, 2, 3, right? That doesn't matter for B, right? We could say that, you know, we could then say A is a subset of B, right? A is a subset of B, right? All the elements in A are in B. We could also say that 3 is a element of B, right? We can say all those things. So we can say that thing. We also can do something like this. Let's redefine B again. Let's go ahead and say 1, 3, 5, right? We've got the union operation that we learned about, right? You're not going to be really tested on these, but because you've already been tested on these, right? But A union B would give you all the elements in A and all the elements in B. Now, we aren't going to call it union in Java for some reason. We're going to call it like, if we do this, it would be A.addAll B, right? Because they like to use terminology. You'll see. But the answer would still be the same. 1, 2. The resulting set would be 1, 2, 3, and 5, right? And 1 doesn't appear twice because things don't repeat in sets, right? Things don't repeat in sets. If you were to do the opposite operation, kind of, not really the opposite, but if we flip around that union sign and turn it into the intersection sign, right? Then we just have only the elements that are common between A and B, right? Which is just 1. So it's all the same operations here. No real need to dig into them too much, right? So, but that's the type of set we're talking about. There's one other operation, the set difference, but I'll remind you of that. So sets and maps they provide these, again, it's all about efficiency. These things are constant time things. So a set you can implement in 2 ways. So we're specifically, when I'm saying they're constant time, we're talking about the hash set. A tree set, remember I said that for hash sets or anything you build with a hash table, anything that uses this constant time like lookup that sacrifices a bunch of memory, that will be using a hash set, and that means that we don't care about order. That's another consequence. We just don't care about order. If for some reason you have to care about order, then you can implement it as a tree set, which will implement a set just using a tree, which means all the algorithms use log n time rather than constant time. And that's, if you need to keep things in order, it's perfectly fine, but we're going to be basically learning about hash sets here. Okay. So again, you can have yes.
So a tree set can't have the same values.
Right. It wouldn't have the same values. Right. It's a tree. Yeah, it's a tree that would be implemented as a set, and it would basically be keeping things in order because it's a tree, you know. Hash sets, as you'll see, don't really care. Okay, so it has union. It implements union, intersection, difference, and subset, and you can add and remove stuff. Right, and it goes through a bunch of examples here that I just went over on the board, just with more complicated. The only thing I didn't go over was the set difference, which is like removing all the elements from A that are in B. So 1, 3, 5, 7 minus 2, 3, 4, 5 is 1 and 7 because you're removing 3 because it's in both of them, and 5 because it's both of them. Okay. The big thing, so let's go ahead and go over like the operations, like actually, making them. So let's go ahead, project, code, new package. Let me enter a new package name. Hash evening, okay, and new class sets, okay. Public static void main. Whoops. Here we go. Public static void main. So the first thing we're going to do is create our set, and it's going to be a set of strings, okay. So set of strings. Right, so it's a set that holds strings, right, rather than numbers here. And we're going to call it set, and we create a new hash set, just like you would do list. List is equal to list is equal to a new list. This is the really boring part. I'm sorry about that, but there's really no way of getting around that. So Okay, so now we need to put a string here. Okay, and then it says, hey, cannot resolve the symbol. I'm sure you can if you were to import it. Java.util. So we just need to import this now. Import a set. Okay, now we've got both things. Okay, so we've got our set. We've got our... and now we can do stuff like set dot. How do we add stuff to a set? Well, let's go ahead and add hello. So set dot add world. Just like all the other things, this has the random boolean that we're going to be when we add elements to it. Oops. So when we run this, it's going to go ahead and say true when we added something to the set, right? Just like a list, right? It's going to return true whenever we add something to a set. The difference is that sometimes this that actually it's not random here. There's a reason that we return true and false, and that's because sometimes adding things can fail. Remember, sets can only have one copy of anything in it. So if I do the same operation twice, try to add world to this set again, if I run it, it'll say true the first time, false the second time because it's already in the set, right? So it will go ahead and just stop. All right. So what's so it returns true if it can add it, returns false if it can't because it was, and the only reason it can't is because it was already there. So let's go ahead and just go back to just adding this. So hello world, okay, and let's just print it out. Sout the set, and it's not going to look like anything special here. It's going to get me world hello. World hello. Maybe it's adding things in different orders, right? So maybe because I did hello and then I did world second, right? The world, maybe it just puts stuff in front. Maybe it works that way. Let's go with foo. Let's go with let's try a bunch of different words. Foo, bar, set.add, baz. Okay. Set.add libel, and then wobble. Okay. Now if we run this, let's see how things are stored in there. It's stored in bar foo. It's got bar world foo baz hello wobble wibble. The order is just completely random, isn't it? Right? There's no rhyme or reason to it. I mean, there is. You're just not. It's just that it's all hidden from you. But the important thing to know is that you're never really going to be able to predict the order things come in that things are stored in the set in. It's completely deterministic, meaning it's a non-random process. There's in other words, there's a algorithm that we're going to learn about, which is called hashing, that does this. But from your perspective, order is irrelevant. Order does not matter here. Okay? So, and internally order doesn't matter. In fact, I can't even iterate through this thing using like a regular for loop. Mind you, you can't do that with a tree either, but these things, unless you build an iterator. But here we need to actually use like a for each loop. So like for string word, if we want to print out each word line by line, we would need to do for string word in our set. Sout word, right? I have to use the for each loop to go through each thing in this, right? If I want to print them all out line by line. If I want to go through everything in the set, I have to use a for each loop. There's no for int I in this one, which is both a blessing and a curse, right? So, okay, so what kind of use is it? Well, the set really works really well as for anything where you need to use like a kind of a tally or a check mark. Not necessarily tally, but like basically checking off to see, have I seen this thing before? If I have, put it in the set. Sorry, if I haven't, put it in the set. If I have, then that probably tells me something, right? A good example is when we were going over all the way back. We were going over something like when I was going over Big O, it was like, okay, given a word, test if all the characters in the word are unique, right? So public, static, Boolean are unique, which basically tests are all the letters in the string unique, right? String word. So are all the strings in this word unique? And the thing we would have to do is that basically if this was a list, or, well, it's a string, but basically you're thinking, okay, so I have to iterate through every character and test every character against every other character, which takes, so I have to test each of the n characters against the other n-1 characters, which takes O of n squared time, right? Here, though, if we use a set, we can do this in linear time, in O of n time. So here I'll use set set scene characters. So I'm going to create a set of characters called scene characters, equal to new hash set, okay, of character. Okay, so it's a bunch of characters, and if we get to the end of this, I'll just go ahead and return true. So I'm going to assume that all the letters are unique until I'm proven otherwise. Okay, so for car C in word dot to character array, I'm just going to go through it as a character array and just turn it into that thing. Okay, if scene characters dot contains, let's go ahead and do if scene characters dot contains C. So if we've seen the character before, return false, because we've obviously seen it before, right? So if we've seen the character before, right? If the character we're checking is in scene characters, then we've seen it before, meaning all the letters aren't unique, so we return false. Otherwise, if we haven't seen it before, well, haven't seen it before, so now I've seen it. Scene characters dot add that character, and that is it. I just simply go through all the characters in the word. If I've seen it before, return false. If I've seen it before, return false. Otherwise, add it. And if I get to the end, return true. Yes.
Could we also check if .add returns false?
Yes, we could do that. I was actually thinking about doing that, but I didn't want to make people have to remember that was what the case was. So if I do, if scene.add, so basically I can do this in a much shorter statement. If I add this character to scene characters and it returns false, meaning I wasn't able to add it because it's already there, then I want to return false. Right? That's exactly right. And don't mind that basically, and yeah, my font's a font that basically is combining these characters into a single character. So it is actually a double equal sign there. It's just stretching the characters. So okay. So this seems like a pretty useful tool. Basically, being able to keep track of stuff that I've seen very easily in a data structure. That's really nice. There's a lot of uses for a set. Okay, and again, basically anything that for over a single item takes constant time. But if you're going over all the items in the set, of course, it's going to take O of n time because you're going over n items. Okay. So this next part is again they've got this whole thing here with the set interfaces and methods. The big thing to compare lists and sets, I don't think you're going to get them confused. I think the authors, for some reason, think you might get them confused, but I don't think that's the case. Sets only have unique elements. List.add sometimes will always return true. Set.add sometimes returns false. And lists do not have an index. Sorry, lists have an index. Sets do not. So you have to use the iterator for it. So now that brings us to maths, which means I'm going to go completely off the rails from the slides, actually, because I'm going to go ahead and boot up Python instead. So I'm going to use what's called a REPL in Python, which is read, evaluate, print loop. So essentially what it's doing is it's as though it's reading a program and executing it line by line. Okay, so now you got, first I'm just going to explain lists for a second. Python does not have arrays, it has lists. So like here's an L, and let's create the list of 1, 2, 3, apple. Python's a weakly typed language, which means it really does not care what you put in it. So that's both a blessing and a curse, because it makes it really easy for you to forget what types the variables should be holding. And since it's weakly typed, meaning any variable can be any type, right? So I could turn L into a, really big number, and it's perfectly fine with that, right? But if you forget that you changed it to a really big number and you thought you had a list, you might be in an issue. You might be having a problem, right? So both a blessing and a curse there. So, right, just like in Python, just like in Java, I can't say L4 is equal to 5. I can't add and just randomly do something like that. I have to actually use an add method, L.add. Only in Python it's called append. So I would append 5, and now you've got 1, 2, 3, apple 5, right? So, but given this index, but basically the way it works is like, here's my list. Given this index, return the thing associated with that index. Okay? It's a fairly straightforward process to understand, right? We just don't necessarily always think of it like that. So like if I give L 3, it's going to return apple because that's the value associated with index 3. We don't think about it that terms that often, right? We normally think of it as the value stored at index 3, but when we're dealing with maps or hash tables, it's useful to think of it in this term. We're creating a mapping between two items. So lists contain basically, you've got a continuous mapping. You've got 0 through some number index, right? And all those values go to some all those keys go to some value. All those indices go to some value. Dictionaries, on the other hand, are way more freeform. So I've used a bunch of terms here, but they all mean the same thing. Map, hash table, dictionary, they pretty much mean the same thing, although hash table is technically what you use to build them. In Python, they're called a dictionary, and you initialize them like this. Now, dictionaries are kind of weird at the first glance, but they use the same notation as in Python, which is why I like to go over them first, because you can use the same notation as lists. D3 is equal to hello. That did not crash, even though it's kind of empty. D5 is world. So this weird dictionary thing that I just created, right? It's got two values there for it. It's got, I've created two key value pairs, is what it's called. We've got basically the key 3 and the key 5. Key 3 goes to hello, key 5 goes to world. So not too much. So that seems a bit weird. But, I mean, it's not really any different than the list we were just looking at. Like, 4, if I put in 3 for list, I get apple back, because that's what I stored in the list. Here, if I say D3, I get hello back, because that's what I told it to associate with the value 3. What if I ask for D2? It's going to tell me you didn't associate anything with the value 2. Okay, what about 4? Didn't associate anything with 4. What about 5? Yep, you did. So basically, what this is kind of it's a generic, it generalizes. It's a generalization of this entire idea of a list. This entire idea of given an index, give me the value stored at that index. Here it says, give me a key. Give me the value associated with that key. And those things can be anything. That's the really awesome thing about this. Right? D blue. So now if I give it the key blue, it will return the value associated with blue, which is, that's normally the color of the sky. Okay? So not only can I use a number here, I can use a string here. I can actually use pretty much anything. Yes? You can use, it's the rule for maps as well in Java. So you're going to see basically there's essentially 2. So here we have, now first off, we have D. So let's go ahead and just see what we've got here. So we've got 3 keys and 3 values. We've got 3 goes to hello, 5 goes to world, blue. So we've got the pair hello, 3 hello, 5 world, and blue. That's normally the color of the sky. We can also do 2 is equal to hello. So now we've got 3 hello, 5 world, blue. That's normally the color of the sky, and 2 hello. So we've got a bunch of, so there's a couple rules here. First off is basically I've got 4 different keys and I've got 3 different values. The same values just stored twice in 2 different keys, right? Both 2 and 3 store hello. Okay, and I can basically use anything as a key, as an index to this thing. Okay, basically anything gets turned into an index. Now, some of you might be asking why. Like, why is this a thing? Why wouldn't you just use like an array? And the answer is because this generalization is extremely powerful. The homework that you are currently working on, the index tree, is trivial if you use a map instead of a tree. It's completely trivial if you use a map instead of a tree, because what you use as a key, I mean, with the current one, we're basically saying store all the words, and for each word, I would like to keep track of the number of times I've seen it, and a list of all the times I've seen, and the list of all the places I have seen it. So the key in this case, I could set it up so that every word is the key, and the associated value is an object that holds the number of times I've seen it and the list of words. And so I just say, given this word, give me all the information about it, and it would just give it back to me. And this is essentially what you're doing with a tree. The only difference is that basically maps are completely designed for this. So yes. How do I traverse over that? So let's go ahead and say for k in, so for every k, which is the key, in D, which is my dictionary, this is the for each loop in that. So let's go ahead and just print k to see how this loop works. So I can traverse over all the keys. So it gives me all the keys. So 3, 5, blue, and 2. So I can, if I go over this again, I can do something along the lines of print D, the dictionary, given the key, and then I can get all the values that way. And I could also do it so that I do both. Print 3 hello, 5 world, blue, that's normally the color of sky, 2 hello, right? And the order, again, that seems to just be the order that I added things in this case, for the way it's holding it. So let's go ahead and go over the maps. So the map is kind of related to this set, a way to understand it. You've got essentially 2 sets. You've got mathematically speaking, you've got 2 sets. It's a set of ordered pairs, right? You can think of it as kind of I'll go back and you can think of it as terms of functions, but a map is just a set of ordered pairs the elements are known as a key and value. You've kind of got this concept. You normally don't think of it like this, but if we define a function like f of x, right? Define f of x and as so the function f of x is equal to 2x, right? We're setting up a key value pair, right? That's the domain range kind of thing. If I give you 1, you're going to give me 2. If I give you 5, you're going to give me 10, right? The key is the input is x, the value is f of x. So that's kind of a way to do. So a mathematical function kind of just creates that association all in one go. Here though, with a map, in a computer science, we just create that piecemeal. So a map is a set of ordered pairs whose elements are known as keys and values. So the big thing is that the keys need to be unique, the values do not. Okay, so what happens if I do something like if I don't make it unique? So we have already defined blue as that's normally the color of the sky, but what if I do D blue is equal to A? Well, what it does is that it updates and overwrites the previous value. So now if I print out D, it will be 3 hello, 5 world, blue, A, 2 hello, right? So the keys have to be unique. The values don't necessarily have to be unique. A a lot of, just like a function, if I did the value f of x is equal to 5, all the keys have the association, are now associated with 5. You can have as many keys as you want to be associated with a single value. We're essentially mapping each key to a particular value. So, for instance, here J is mapped to Jane, B is mapped to Bill, B2 is mapped to Bill, S is mapped to Sam, B1 is mapped to Bob. It's a many-to-one mapping. Okay. In an on-to mapping, so basically it's also on-to in the sense that every element in the value set has a corresponding key. So you can't be just a value hanging out by yourself. You've got an associated key. So there's essentially just, and other than the add and remove, we've got, add and, so well, here's the typical function to use. You have put and get. So we put the key, some key in and some value in, which can be different types or they could be the same type, and then get to retrieve a key. So let's look at some examples of what keys are in the real world and understand, like, why do we care about what a key is? Okay, a key is typically, in computer science, when we say a key, it's a unique ID number, right? You have a unique ID number. That's actually the first example on this table, right? You've got some student ID, I've got some faculty ID, right? And over here it's got a number, right? That's my unique ID number that identifies me. Now, are you given a unique number because the university is a faceless organization that views you as a bunch of dollar signs to turn you into a bunch of diplomas in the process of acquiring a lot of money? I mean, you can certainly feel that way sometimes, right? But no, you get a unique ID not because you're a part, but because your name is actually kind of useless in the university system. I went to middle school, and when when I arrived, they kept asking me, "Are you related to Andrew Rosen, the guy who just graduated from 8th grade, and now is out of the school?" I'm like, why would I be related to somebody with the same exact name as me, right? Okay. No, I mean, but it goes to show basically, that's a small geographic area. People are going to have the same name as you. You can even have the same birthday as you, right? I mean, so you can also have the same name and the same birthday, right? So your name is not a unique identifier. Neither is your address. Neither is your name plus your address, because it's possible that it is possible, albeit highly unlikely, that two people with the same name occupy the same address. It could happen. Things like this happen, 1 in a million chances happen 9 out of 10 times. So, it happens a lot. So, your major is definitely not a unique identifier. Like, everybody's in here of 1 or 2 majors, so you're pretty much guaranteed to, unless you're the only person in either a CS or IS&T, I highly doubt that, you're sharing your major with somebody in this classroom. Your grade point average is probably not unique, right? Given that basically we round up to 2 digits, right? So you've got a, x point yz, right? Somebody probably shares that x point yz value with you, right? So what can we do to make sure that basically when we're talking about a student, we got the specific student? Because that's really important because of something called FERPA, which means the Federal Privacy Act for students, right? That means that basically that when you go and say I'm Andrew Rosen, to your advisor, you're like, are you the Andrew Rosen that lives at 123 Alphabet Lane? And you go, no. They just violated federal law because now I know there's an Andrew Rosen who goes to the school whose private address is 123 Alphabet Lane, which may have been privileged information, right? So it's very important that we deal with the right student. So that's why when you do a lot of interactions with administration stuff, they don't ask for your name. They ask for your email or your TU email or your student ID number, which is a unique identifier for you, right? So here, the unique identifier number, you plug that in and then pops all the rest of the values. So your key here is your student ID number. The value is like an object. The value is an object that holds your name, your address, your major, and your grade point average. Don't need to store the key in the value. Don't need it because key gets you the value. You don't need to store that necessarily in the value, although you can if you want to. So another thing for a more business-oriented thing is online store customers. Say you're working at, you're on Amazon. How does Amazon keep their, one customer separate from another? Can't rely on the name for the same reason. Can't rely on the address for the same reason. you and somebody else probably share an address. Credit card number can't use a unique credit card number because you can share your credit card number with like a parent or a sibling or a spouse, right? You can, you might have the same credit card number as basically as another person because you're both on the same credit card. Shopping cart, certainly not. Your shopping cart, it does not uniquely identify you, right? But it is information that you definitely want to keep associated with you. So typically what identifies pretty much everybody uniquely on the internet is email address, right? An email address is pretty much unique to you because you're the only one who has control of it. And so that's one way to keep basically multiple accounts separated. Now, you might have multiple accounts and that's perfectly fine, but to keep those accounts separate, you use an email address and sometimes you use that to get a username. Okay. So the email address in this case is the key, and it retrieves your name, address, and the credit card information that's needed to make payments and your shopping cart. So basically having a key, if basically giving you this key, either the email address or the student ID number, gives you all this stuff in constant time, that's huge. That's actually kind of necessary if you've got billions of customers, right? If you've got billions of customers coming to your website, billions of accounts, you need to be able to get that answer in linear time, not in linear time, but in constant time, because if you got it in linear time, that's going to take a while. You have to iterate through a billion accounts to find the right one. And, you're not just getting like one request a minute. You're getting these multiple thousands of requests, possibly a second. So definitely need that to be as fast as possible. Okay, so obviously these maps have really complicated operations, and it's probably got like 2,000. Fortunately, that's completely wrong. We have only 5 operations that you need to know about for maps. Maps are really dirt simple when you get right down to it. First off, and we can basically throw this one out. Okay, that was weird. Okay, super sensitive mouse wheel. Okay. So we've got 5 operations. We can throw this one out. It's size. It gives you the number of key value pairs in there. Okay, that's not too complicated. Boolean is empty. We can also throw that one out. That's as like having to like memorize it or anything. It's not a complicated one. If it's empty, it's empty. Okay, that's pretty self-obvious. So you've got really 3 kind of methods that define it. Put a key value pairing in. So put the key value pair and it will return the value associated with it. Remove, so you can put in a key value. Remove the key value pair by just providing remove the key, right? So you say, given this key, please remove any, please delete the association between this key and this value, okay? And the last thing is get, which says, given this key, get me the value associated, which is a very common operation. And all these things will somehow take constant time to do. So how in the world do we do this? Well, first let's just go over how the heck do we use this thing. Okay, how do we use this? Well, let's go ahead and just comment out the set stuff, and I'll create a map instead. How do you use this in Java? Right, we saw how to do it in Python, but we're not in Python right now. But this exists in almost every single programming language in some way, shape, or form. So a hash set, not going to add the generic, sorry, we're going to say not a hash set, a map. So map is equal to a new hash map. Now I'm not going to add the generic, so I'll add the generics in a second. So, but the data type is called a map. Okay, so come on. I'm sure you know how to. Oh yeah, Alt Enter, and Alt Enter to do the import the class. Okay, so we've got map is a new hash map. Now, unlike other collections that use a single generic like E, right? Maps use K and B because it has 2 different data types, right? It's 2 sets, remember, a set of keys and a set of values. So we might have something like string and integer. Okay, and we might have a hash map between string and integer. Right, so the string is the key, the integer is the value. All right, so to add something to it, we just do, to put a key value pair, we would just do something like, here's the key, put in this key, K, hello, and then put in a value, 0. Map.put map.put let's go world 1. Okay, so what kind of use is a map in this case? Oops, that's out. Map. So what kind of use is a map? Hello. So here we've got world 1, hello 0. What kind of problem can I use to solve this thing for? Well, the common thing you can do, one of the most common things I use this for is counting words. Not counting the number of words, but counting how often each given a string, how often something occurs. So let's say we're given so let's go ahead and say public. Say we want to figure out what the most common word in say we're given a bunch of strings, right? Like a huge document, and I want to find out what the most common string in that document is, okay? Or maybe the 5th most common or something like that. How in the world would I do that? Well, the most common is pretty easy. Easier to do if you've got a map. Because what we're going to do is that we're going to count up how often each thing appears, right? Now, so let's go ahead and do that. Public static string most common string in an array of strings. So int. So let's go with a string array. Words, right? This is a bunch of words. Let's figure out what the most common string in this array of strings is. Okay. Well, what we'll do is we'll use a map to solve this problem, and we'll do a string. It's a map of strings to integers. Now, each word is going to be the key. So each string is going to be the key. What is the value going to be? The value will be the number of times I've seen it. So initially, it's just going to start out empty because I haven't seen any words, right? So there's not really any kind of association going on. So what do I have to do? I have to iterate through all the words. So for string word in the array of words, so for each word in words, what am I going to do? It's very similar to the checking for things if they're unique. If map.contains key, so there's a contains key and contains value. So if the word is already in my map, so if the word is already in my map, I'll do one thing, and then otherwise, let's figure out. So this is if I've seen the word already and if I haven't seen the word already, right? So I haven't seen the word already. Well, this is the first time I've seen it. So I've seen it exactly how many times? Once. So what's the key? So we can create a key value association for that. Map.put word. Map.put word and put in, and I've seen it once. That makes sense to everybody? I've seen this word once. Okay. If I've already seen that word before, though, then, well, let me see how many times I've seen it. Int times seen would be equal to word dot get. Oh, sorry, not words dot get. Map dot get the word. So get word. This would return. So given the key, which is the word, it's going to give me the value, which is the amount of times I've seen it, right? So now I've seen it one more time than the time I've seen it, so I'll go ahead and update the value in there. So map.put key and then time seen plus 1, right? And this will overwrite the value. Okay? So what's the key? The keys. And what this does, these lines basically count up the number of times. All this does is iterate through every word and basically counts all the times each individual word has been seen. That's pretty powerful for just a couple lines. Okay. Okay, so I haven't done anything yet because I have to return a string. I'm looking for the most common thing. So return the empty string right now. But I can do sout the map. Okay. And then let's just go ahead and try this. So string words is equal to apple, hello, banana, and I'll just copy paste that a bunch of times. So a bunch of hello bananas, and then a world. Whoops. And in a world, and I'll just copy paste banana world a couple times. Okay. Boom. So yeah, I'm just creating a bunch of words that are easy for it to count. And then we'll do, we'll call the function, which was, what's the function called? Most common string. Most common string words. Now, if we run it, I told it to print out the map. It quickly just says, okay, you had 8 bananas, 1 apple, 4 world, and 5 hellos, right? And so what's cool about this is that basically if we needed, so there's a couple ways we can go about doing this now. Basically, again, order doesn't matter in this case, but now we have these key value pairs. We could go through them and we can kind of just sort. We could basically, let's see, what can we do? Can we do map dot, we can get a key set and we can get a, yeah, we can get the connection of values. Yeah, all we need is basically the a string, most seen word, and a val, which is the empty string, and an int most times seen is equal to 0. And now for let's say string word in map dot key set, which is a set of all the keys in there. So for every key in there, if map dot get word, so the number of times I've seen that word is greater than most times seen. Most seen word is equal to word, and most times seen is equal to map dot get word. And now that will return, and now if we return most seen word, okay, we'll go ahead and cut that and paste it in. It should return banana. So now the most seen word is there. So that required O of n time to go through all the words in there, and then O of n time to go through basically all, or then O of k time, which is the number of unique words to go through, which at most was O of n. So this took basically 2n time to do. All right, so I think we can take a break here, so maybe for 10 minutes, and then we're going to learn how in the world do we make these things. How in the world do we make these things? So maybe let's take 5 to 10 minutes to take a small break, because how to make these things is cheating. That's how we do it. We cheat.